Hello everybody, my name is Julien Vanegue. I'm with Bloomberg and Imperial College, and I will talk to you about how I started using Infer and at Bloomberg particularly to find security bugs. And not only using Infer, but also I was very interested in actually extending Infer for new properties. So I will tell you a little bit about my experience there. All right, first of all, I really want to say I want to thank the Infer team because Infer is an amazing framework. Infer has separation logic. It has now incorrectness logic with the pulse checker that was talked about a little bit previously, and also it's written in OCaml, which is a functional programming language, a modular programming language, meaning that when you change Infer somewhere, you don't break everything else around, which is unfortunately very rare in the other frameworks I've been actually using. And so there are two, as you all know, there are two main kind of classes of properties that one may actually want to check in a program. One class of property is what most people actually are interested in is safety. And safety basically means that something that's wrong will never happen. You also have liveness. Liveness is something good will eventually happen. So, of course, in safety, you have all sorts of safety property you may want to check in programs. For example, the absence of array out of bound accesses, absence of use after free, absence of memory leak, etc. Liveness, a very famous liveness property is whether your program terminate or whether your program will do something that is desirable again and again in the future. For example, acquiring and releasing locks and things like that. And when you look at Infer, you see that a lot of the properties are mostly safety properties. So all of those that are have been talked about in the past are about safety. So one of the first question I want to ask the Infer team is, where did you put the liveness checker? And we'll talk about that a little bit today, because part of this talk is to report on a new checker I've implemented in Infer. Called Pulse Infinite, which is a checker that extends Pulse to find non-termination bugs in C and C++ programs. And why is non-termination analysis important? Well, first of all, if you look at the CVE database, you realize that there are tons of non-termination bugs out there, but there is no clear non-termination bug finder. There are tons of programs, tons of analyzers that are trying to prove termination, and some of them also try to prove non-termination. However, what Infer and Pulse allows us to do here is to have an under-approximate non-termination checker, which is not quite out there yet. And so what's really interesting as well when you look at those non-termination bugs is that they affect all programming languages. It's C, C++, it's Java, it's Python, it's Rust, it's, you get it. And it affects also very, very mainstream programs like the Linux kernel, OpenSSL. Many of them actually have no non-termination bugs in the past few years. So that makes it really relevant for someone like me to actually go after those bugs as we're getting into the memory safety realm or the memory safe programming. We realize that non-termination is still a major issue that people have to take care of. And this is actually a little bit appreciated sometimes. Not only that, not only those bugs are present in a lot of different programming languages or programs written in a variety of programming languages, but also the trend is going up. If you track the non-termination issues, like the infinite behaviors in programs since 1999, thanks to the CVE database of MITRE, you realize that these keep going up. And so, as we, even this year we found, by we I mean the community found about 60 bugs already, which is pretty much almost as much as last year at the end of the year. So people keep finding more and more non-termination bugs, but they get lucky. They find those bugs by getting lucky. Maybe the user actually discovered one such bug, but there's no systematic tool that can be used at the very large scale to find these kind of bugs. And that's where, that brings me to the core of my talk, which is really how can you actually use Pulse and Infer to find non-termination bugs. And we created this new program logic called Infer, which stands for under approximate termination analysis, with work with Azalea Rad and Peter O'Hearn. And I'm happy to report that it's now accepted at OOPS-Lab 2024 with minor revisions. And just very briefly, how that logic looks like. Just going to mention a few rules here. We introduced this new notion of infinite triple, right? Where we're able to actually have a similar like OR style logic, except it's under approximate, so I should say it's incorrectness style logic here, dedicated to finding divergence bugs. For example, the sequential rule at the very top, say you have a couple of code fragments, C1 and C2. The first one goes from P to Q, and the second goes from Q to a divergence. Then obviously, if you sequentially compose C1 and C2, then that diverges. If you have a choice, say an if-else, a conditional behavior, and you know that one of the if or the else actually diverge, then you know that the entire conditional diverge is a diff choice rule. Similarly, if you have a loop, that's an interesting one. Or a repetition, it's really a repetition rule here. Say you have a piece of code C, it goes from P to Q, but Q is inside P, meaning that the set of state that you discovered is a subset of the state that you started with. Then repeating that piece of code diverge. And finally, if you have a while loop, the while loop while BC. So you have the piece of code C that goes from P and B to Q and B, and again Q is inside P, then putting that piece of code C in a loop guarded by the Boolean or the predicate B diverges. Yes?
What if Q is false?
Yes, what if Q is false? It's a good question, because if Q is false, actually that's a valid under approximation, and the premise is actually still true that wouldn't diverge. Good point. Any other embarrassing question? So, by the way, I just came from New York yesterday, so if I fall asleep before you, that's fine. All right. And so, just this small tool that we created, Pulse Infinite, based on the wonderful work of all the meta team over here. We've actually evaluated this on a few million lines of code so far, and we found 21 bugs. And when I say 21 bugs here, I'm not including false positive or anything like that. Our signals ratio is around 30% at this stage, but we're working very hard to actually make it better than that. So we were able to find quite a number of issues, and we reported those issues so that the community can benefit from our work. A few examples. OpenSSL, you have this function called AES-ECB cipher. You have this function, this loop on line 10. You can see what it does is that it iterates over an input buffer, and it goes from BL to BL bytes. The problem is, if the context is null in the call of EVP ciphers context OpenSSL get block size on line 5, then BL will be 0. If you do plus equals 0, of course, the root does not make progress, and you have an infinite behavior. Another example, in libxml, you have a dictionary, right? The old entry, those variables are initialized as such. As you can see, you have this old entry pointing to the beginning of the dictionary table, and then old end pointing at the end of that table. Well, you have these conditions kind of bizarre on line 9. If that's true, the old entry gets reset to the original value. So you can see that if this condition is ever entered on line 9 and 10, then the loop is going to come back to the original state. So when I reported this bug to the libxml folks, what they told me, oh, but this condition is never entered. It's dead code. I'm like, well, if it's dead code, you should probably remove those lines then. Yet another bug. In CryptoPP. CryptoPP is a small C++ cryptographic library, and it has wrappers for dynamic memory allocations in this aligned allocate, and that's quite a common actually source of infinity or divergence. It keeps trying. If malloc fails, it keeps trying forever. That's what I'm suggesting as a fix here is to have a counter, and if that counter reaches a certain threshold, then you should actually stop and say, you know what, there's no more memory, it's pointless to actually continue, we just want to exit the program. All right. Interesting, when Peter O'Hearn actually provided this piece of code to LLM, the LLM was able to find the bug as well. Pretty interesting. All right. This is a little small, so I apologize for this. This is how, so we talked about the what, we talked about the result. Now I want to talk about the how a little bit, and I want to pass a few minutes on this. And I realize I'm glad I'm actually presenting this to realize how small that actually appears on the screen. And if you look at the implementation, how this Pulse Infinite tool is actually implemented, it's implemented as such. First of all, there is a little extension. There are a number of different components in Pulse. You have the main Pulse, of course, the main Pulse file, PulseML. You have the abstract interpreter.ml, which is colloquially referred to as Infer.ai. Then you do have the Pulse formula, which is a solver in Pulse, okay? Like Jules mentioned previously, was really it's kind of an SMT solver without using an SMT solver. It's very, very fast. And then you have the Pulse execution domain, which is some core part of Pulse where the Pulse state, or it's not called Pulse state in the code, but I just renamed it as such for clarity. Where those Pulse states, the types of Pulse state are actually tracked. So let's go through a little example. I'll have a pointer here. No. Okay, great. I'm sorry. That's what happens when you actually click on buttons you don't know about. All right, so here I can actually read it properly. Here's how it works. First of all, whenever you have one of those prune seal instruction, that prune seal instruction leads to a call to prune binup in the Pulse formula part of the code. That Pulse binup, you can see on the top here, what it does is that it takes the path condition and then it adds a condition that the prune actually just send it, and just add these to the path condition typically, which is part of the domain of Pulse by default. One of the things that I added there is to make sure that condition, this particular condition that we extracted from a conditional or from the loop predicate, is actually not optimized in the Pulse solver. And I'm going to show a bit later why, when this can happen and why this is a problem. But this is really important that this particular condition is not optimized out. The reason for this is because we want to be able to find those cycles, right, in those lasso properties, as we call them, when, on our small example here, when you have, say, a small loop while x is smaller than max, if x different than 100, x plus plus. Well, obviously, this is going to iterate a number of times, but when it reaches the state where x equal 100, it's not going to increment x. That's just a toy example to explain. And then what this results into is a state space where you get into a state where x equal 100 and you just have a loop on that state. So it gets to an infinite diverging behavior, right? And so for every instruction, we're going to have this exec instruction on the very top left here. And for certain kinds of instructions, say the if and the while, it will actually call into this prune binup. So all good, we collect a bunch of constraints and we add this to the Pulse state. Then, for every loop, we're using the widening primitive of Infer AI to do something fun. So as it was mentioned in the previous talks, the widening of Infer AI can be abused, and it is abused by Pulse to be under-approximate rather than over-approximate, as you would expect for an abstract interpretation framework. And so what we do here is, in fact, we do a k-bounded unrolling of the loop instead of actually trying to accelerate convergence, as you would normally do with a widening operator. And so what happens there is that the widening, we added these transfer functions, let's call it like that, package, and that package is implemented in this execution domain. What package does is simply that it computes a work set. The work set is computed over there as just the new states in the pod that are not already present in the pre. So for every new state that have been created, we want to detect a lasso. Lasso as a cowboy lasso when you're going to, like, you're looking into, like, to catch a goat or something, and then you, like, bring a lasso around the neck as it's running, and then we want to find this lasso in the state space, meaning that we came back on a state we've already seen before. So we compute this work set, and then for every state of the work set, we try to see if any of the state was actually already known. And the way we do this is to having this hash table we call the widened state or widening state, and that hash table is actually indexed by a triple. The triple is the raw equations that we collected through our prune collection on the top here, then the path condition which was already there in Pulse, and finally the location of the loop. So for every loop in the program, we index the widened state through a path condition and the raw equations. If that index was already in the widened state, it means that we already found a state that was equivalent, at least according to those parameters, to what we've already seen before. And then what we do is we create a new state infinite program, which we added to the list of types of states that Pulse has. And if it's not, then we simply add the state into the widened state at this index, and then we try to detect the lasso on the tail of the rest of the work set. So that's roughly how it works, omitting tons of implementation details, of course, but it's basically how that works in Pulse Infinite. Any questions?
I guess kind of an implementation detail question. When you're extending Pulse in this way, do you kind of have to modify it, or are there ways where it's designed to be extensible, say, to track these raw, the raw EQs information in the formula and that kind of thing?
I had to modify Pulse in about 150 files. So, to answer your question very shortly, if we had a mechanism that could allow us, of course, to extend Pulse without changing the core of the code, that would be great. I don't think such a mechanism exists at this stage.
So here in your work sets, you keep track you don't keep track of the shape of the memory, or like a lot of the state of Pulse is gone at this point. So it doesn't really implement the rule you showed earlier, right?
It's slightly different in how the rules are implemented, which means that the rules are actually only covering the variables appearing in control predicates. Okay, let's keep going. So we're getting to next section of my talk, which is my laundry list of features I'd like to see in Infer. And so that's quite interesting because that is driven by a very concrete application of Pulse on very large code base, which I typically see is leading to either unsoundness or incompleteness of the analysis, particularly in this new checker. But I have a hunch that this is actually a problem for more than me. First of all, the Pulse optimization can hide bugs if you're not careful, which motivated some of my changes there. So let's see this small example. If you have a very basic loop that do not terminate, say int x equal 1 while x different than 3, y plus plus, obviously x will never be equal 3, and so you have an infinite loop in this particular case. You would like to see this bug. However, pulse is smart enough that it recognizes that x is always equal to 1. And so it optimizes this by saying while 1 different than 3 instead of x different than 3. And it further optimizes by true. And so, in fact, the way it means that there is pretty much an empty path condition that is being tracked there. And therefore, the cycle can goes from an empty path condition to an empty path condition if you're not careful, because those conditions were optimized away. Which it's the point of my raw equations with the additional part that I added in the pulse formula solver is to make sure that those conditions do not get optimized away. So I can actually go from x different than 3 to back to x different than 3. Yes, there is a cycle in the state space which is not using an empty path condition. So if I have an empty path condition and I tell there is a bug, there's tons of false positive everywhere, so we can actually do that. And so it's very important to make sure that when you are detecting a recurring state using a logic like that, then those path conditions are not empty. And so those raw equations allow you to do this to make sure that when you are having loops that are, or even like conditional code that is maybe a bit trivial sometimes, then you don't actually optimize away those conditions. And this is part of my branch. Another part that I would like to do in the future is to detect non-termination bugs in recursive functions. Right now we don't actually support that, and there's a number of CVEs, like publicly known vulnerabilities that are actually non-termination bugs due to recursive function or uncontrolled recursive functions. One of them is in sklearn, which is extremely popular machine learning framework in Python. And so we would love to see a better support for recursive function. I've seen some movement recently by some guy called Jules Villard, where possibly the recent improvements of recursive function support will help us do that. To my knowledge, and I haven't really taken a look in very deep detail to these changes, it doesn't really try to detect a recurring state here. It's just more of a syntactic kind of like hint, right? So there's more to do there, but this is going in a good direction, where in the future we can imagine that we'll also support these kind of non-termination bugs as well. Yes.
My question is about the previous slide. I'm confused because I would think that if now the example is while true do something, you would like to catch it with your analysis?
So yes, however, the way that it works is that the path condition in the pulse state gets set to empty. And so that goes from empty to empty when you actually optimize out those conditions. Because then you have no constraint to track. If you say, oh, it's true, then I'm just removing that constraint from the path condition.
But it means that now currently with your prototype, you will not catch infinite loop like while true do something? Because
there are a couple different modes in the tool. One mode is more noisy, where I find those bugs, but then that leads to a bunch of false positives. So I have another mode that remove those trivial lassos, as we call them, and then we don't find those bugs, but then the signals ratio is much better.
Yeah, about that, I was wondering what kind of false positives do you get in those? What's wrong about these empty path conditions?
Oh, yes. If you actually, well, it's those trivial lassos, right? If you start saying, oh, I'm going from a state that has an empty path condition to another state that has an empty path condition, therefore infinite loop, that's not quite accurate in pulse.
But like in practice, what kind of false positives does that give?
I would have to look through.
Okay.
Sorry, at a higher level question, what parts of pulse do you most benefit from in this analysis? Like, is it the pruning of infeasible paths that's built in, or is it the memory analysis, or why was it good to build on top of Pulse, like this analysis?
Great question. The two major bonuses when you're using Infer and Pulse generally, it has separation logic in it, and it has incorrectness logic in it. So you can do path dropping, right, under approximation, and also you have a very precise memory model based on separation logic that allows you to not make any approximation on that. So this is really, to me, one of the key reasons why I like Pulse a lot is because of that. The third version, also the third reason, is because it's in OCaml. The fact that it's actually written in OCaml, at least to me, is an advantage. For having actually developed a number of static analysis tools in C++ in the past, you're really like, you know, killing you, like banging your head on the wall when you have a bug. Well, those bugs in Pulse, well, when you get to the point where your code compiles, then you have a really good hunch on the fact that your code is actually going to work. It's not always the case, but it gives you such a huge heads up. Okay, another really great improvement I like to see in Pulse is the ability to reason about bit vector arithmetic. or generally, not talking about bit vectors, since like being told no, it's just the ability to reason about bounded arithmetic, right? Not necessarily bit vector, like bit precise, but if you could reason about bounded arithmetic, you would avoid incompleteness and unsoundness. So let's look at those examples. I have a very basic stuff where you know, I have false negative or false positive in a termination analysis because of the absence of that. Top example, you have int I equal, you know, max u int, and then while I is different than 0, I minus equal 2. Well, because you're unable to reason about either integer overflow or integer underflow, then you will actually not actually you will not actually found. I'm sorry, it's mislabeled. Should be the other way around. But the absence of support for integer overflows and underflow really leads to missing bugs and also sometimes giving false positives. So let's look at the other one here. This is a false positive example where you have this condition while y is bigger than max int y plus plus y minus minus. So just looking at that code, you would think, oh, of course, it's going to not terminate. But in fact, this while loop is never entered because y can never be bigger than that. Y is an integer, signed integer. Right? So this signed integer, int y, this while y is bigger than max int is always false. So you can't enter that loop. However, without actually having knowledge of that, it will think that you can enter the loop. Yes.
Okay. Yeah. So that false positive. I mean, why would you write that code? Did you see that in? It's a top
example to actually show the behavior. But I've seen this behavior in real code. Absolutely.
Okay.
As a matter of fact, crypto code has a lot of that. In cryptographic code, you see a lot of bit level arithmetic, and that totally happens, stuff like that.
And in the first example, it's not about modular arithmetic, right? It's you're decreasing an odd number by increments of 2, so you never hit 0.
So I'm sorry, because this example is actually wrong. So so say I plus plus instead of I minus equal 2, right?
No, but I think that's also an infinite loop, no?
No, because then your integer is going to wrap.
Then it's going to be... No, it's still going to be odd. It's going to stay odd forever, no?
So as I mentioned, this example has a little bug in it. It should be I plus plus instead of I minus equal 2.
Fine.
So if you put I plus plus in there, because you're using a rational solver, it's going to keep thinking, oh, you know, it keeps growing, and so that's fine. But in fact, if you add 1 to max u int, it's going to go back to 0, and then the loop is going to break.
Cool, thank you.
Yeah. Okay? So this is probably one of the top, I want to say the top 2 or top 3 reasons, of sources of imprecision in Pulse. And I realize that there may be a performance penalty adding support to this. The truth is, what is the real performance penalty? Because this leads to unsoundness and incompleteness of not only the non-termination checking, but on any checker that you would actually want to actually spot integer overflow, underflow behaviors, which is present a lot in security bugs. You see a lot of those, and the fact that Pulse does not support this is a problem. All right. So I want to ask, is somebody at Meta taking care of this thing? Because it's not a small job, first of all. I recognize that it's not actually a small job to add this. However, this is a needed feature. And we would like to use that feature whenever that becomes available. All right, what are the future plans? We want to do more larger scale evaluation with Pulse and Infer, obviously. We started analyzing the Linux kernel and the Wireshark. One of the things I actually failed to mention when I showed my evaluation is how amazing performance is with Pulse. Look at those at this analysis time. You're talking about analyzing 1.5 million lines of code in about a minute. It's very, very fast. And I take no credit for this. I think actually Pulse does it all for me. But the point of this is to show that I'm not actually degrading performance of Pulse. But it's really, really fast, and it's amazing that it's so fast because it's very scalable and it can be plugged into the CI/CD pipeline easily. And so, coming back all the way, we want to do a larger scale evaluation. The Linux kernel, when I analyze it, it's about 26 million lines of code, and it took 18 minutes to analyze. Super fast, super usable, great. Wireshark, it's about 5 or 6 million lines of code. Also, would love to be able to, review very efficiently the results there. And so there may be some new feature we want to add to combine this with non-termination. For example, there is an initial taint analysis support in Pulse. If we mix the taint analysis with non-termination, we could find not only non-termination issues, but non-termination that is induced by the user. And in terms of criticality, that goes to the top of your list, right? Because, the user can provide me a value that is going to lead to a non-terminating state or recurring state. Well, that's really good. If you find a bug like that, everybody's going to fix it very, 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 very fast. Of course, we want to keep tracking false positives or false negatives. It's really important when you are using a tool at the very large scale, when you're dealing with tens of millions, hundreds of millions line of code. Even if you have a tiny source of false positive, be sure that this source of false positive is going to explode at the very large scale. So tracking every single source of false positive is really, really important when you aim at actually deploying a tool like that to hundreds of millions of line of code. And finally, once to the point where we are extremely good at signals ratio, we're not 30% or even not 50%, but we're more like 80%, we want to start adding more detection logic where we don't want to compromise on the number of false positives, but we want to find more and more bugs. So that's what we're going to do in the future. Thank you very much. I'd like to thank Peter Ohon and Azal Erad and Jules Villard for their guidance and collaboration. You can actually check out my code. It's open source on GitHub, and you can contact me with any questions. Thank you.
Hi, this is really cool. So you can have denial of service attacks in cases where the behavior is, doubly exponential in the size of the input, but not non-terminating. Is that like a giant gap between what you're doing and detecting cases like that, or is there hope of some kind of extension to your technique to detect, those kind of explosions that might also lead to CVEs?
You're totally right. These bugs actually exist, and there's a number of tools already finding those bugs. For example, the work of Caroline Lemieux she's actually doing some of that with fuzzing, or trying to find like, you know, regular expression code that actually has exponentially increasing complexity that lead to not to non-termination, but that leads to like a almost non-terminating behavior. We're not finding that. We actually leaving it to her.
So it's kind of a different universe.
It's a different property. I would argue. Yeah.
You mentioned you found 21 non-termination bugs. So how many of these were security issues, to come back to the title you talk?
It's hard to say without writing, say, proof of concept exploits. However, some of them were exposed through the outside, some of them were not. So it's a mixed bag. But I did not attempt at writing exploits against these bugs.
Did you file any CVEs?
I'm waiting for these bugs to be fixed before claiming CVEs. But I reported the bugs.
Yeah, did you find examples of errors where you needed the interprocedural part of the analysis?
Yes, absolutely. For example, this OpenSSL bug, right, requires interprocedural analysis. See, if you don't actually have, if you don't realize that if context is null, then it returns BL equals 0, then you can't find that.
And my other question was so about the back test. I mean, in the implementation, when you try to recognize that you have already encountered a pass condition, I'm surprised that you do a kind of equality test between pass conditions, and does it make sense to do an entailment test, so that something is already implied but what you have seen or something?
Absolutely, like it would make a lot of sense to do this, and you found more bugs if you did that. So one thing to remember is that the path condition being optimized along the way by the pulse formula solver sometimes gets simplified a lot, and so the path condition is not sufficient. You have to combine this with raw equations of your predicates along your path, which is not the same as the path condition in pulse because of these optimizations. This said, if there was a way to actually do entailment checking in pulse, I would absolutely use it. After talking to Jules, he mentioned that there's no such thing. However, there is a LEC primitive for states that can be used. So that would be great if I could actually use a facility to just check whether a P implies Q. But I don't think there is such a thing, unless, please correct me if I'm wrong.
Thank you for the nice talk. I have a question about when you asked for support from Pulse for the bit logic. I wonder if what it take for Pulse to support that, and can any of these rules be implemented by you as a user of Pulse to handle this bit logic? And given I am not given
trying to put more work on me, huh? We're in discussion with the Infer team to see how whether or not we have a way forward with that, because it's not a trivial amount of work. This said, there could be simple ways to get most of the behaviors we're looking for without implementing a whole bit vector arithmetic solver. So let's call it work in progress or brainstorming progress.
Thank you.
Any last question? No? Well, thanks again for your time, and find me in the corridor.